In episode 85, titled Generalization, In-Sample versus Out-of-Sample, and Interpolation versus Extrapolation, we step back and examine what it really means for a model to predict reliably, rather than simply fit what it has already seen. Generalization is one of those terms that everyone uses, but many people quietly substitute it with training performance and hope the difference does not matter. In practice, that confusion is responsible for a large fraction of model failures, especially in security and risk-driven domains, where conditions change and rare cases matter. A model that looks excellent on paper can still be brittle if it only succeeds under familiar conditions and collapses when asked to reason beyond them. This episode is about sharpening your intuition so you can tell the difference between apparent success and genuine predictive value. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. In-sample performance refers to how a model behaves on data that is similar to what it was trained on, including the training data itself or data drawn from the same distribution. This is the environment where the model has the most information, because it has already adjusted its internal parameters to reduce error on these examples. High in-sample performance often indicates that the model has sufficient capacity to represent patterns present in the data, but it does not, by itself, tell you whether those patterns are meaningful or stable. In many cases, models can memorize quirks, noise, or spurious correlations and still score very well in sample. This is why in-sample performance is best interpreted as a measure of fit, not a guarantee of usefulness. Fit tells you that the model can learn something, not that it learned the right thing. Out-of-sample performance refers to how a model behaves on data it has not seen during training and that was held out specifically for evaluation. This is where you test whether the patterns learned during training transfer to new examples drawn from the same underlying process. Out-of-sample evaluation is your first line of defense against overfitting because it exposes whether the model's apparent success depends on memorization rather than general structure. When out-of-sample performance tracks closely with in-sample performance, you gain confidence that the model has learned relationships that are not tied to specific examples. When there is a large gap, it signals that the model's complexity or training process allowed it to fit noise. Out-of-sample performance is therefore not about perfection, but about honesty regarding what the model can be expected to do next. Interpolation describes the case where a model makes predictions within the range of feature values it has already observed during training. If the training data included ages from 20 to 60, and the model predicts outcomes for someone aged 40, it is interpolating within known bounds. Interpolation is generally safer because the model is operating in territory where it has seen examples and adjusted its parameters accordingly. Many modern models are extremely good interpolators, especially when training data is dense and representative of the true process. This strength can create a false sense of security because success at interpolation does not imply success everywhere. Understanding that most evaluation procedures primarily test interpolation is crucial to interpreting results correctly. Extrapolation occurs when a model is asked to make predictions beyond the ranges or combinations of features it observed during training. Using the same example, predicting outcomes for someone aged 80 when the model only saw ages up to 60 is extrapolation. Extrapolation is inherently higher risk because the model must extend patterns beyond evidence, and most learning algorithms are not designed to do this reliably. In many cases, the model's output in extrapolative regions is driven more by mathematical convenience than by real-world validity. This is why extrapolation errors can be extreme rather than gradual, producing confident but wildly incorrect predictions. Recognizing when you are extrapolating is therefore as important as evaluating how well the model interpolates. A common and dangerous situation is when a model interpolates very well, yet fails catastrophically outside the training range, because nothing in standard metrics warns you ahead of time. During development, cross-validation and holdout tests often reuse the same feature ranges, so the model is rewarded for smooth behavior where it is already comfortable. Deployment then introduces new conditions, new users, or new adversarial behaviors that push features beyond their historical bounds. The model responds with confident predictions because it has no built-in notion of ignorance, only a learned function. This is why failures due to extrapolation often look like sudden cliff edges rather than gradual degradation. From an exam perspective, the key insight is that generalization claims must always be conditioned on where in feature space the predictions are being made. One practical guardrail against silent extrapolation is the use of feature range checks during inference to detect when inputs fall outside what the model was trained on. By tracking the observed minimums, maximums, or more nuanced distribution summaries from training, you can flag inputs that represent novel territory. This does not require rejecting every such input, but it does require acknowledging increased uncertainty when they occur. Feature range checks turn extrapolation from a hidden failure mode into an observable condition that can be handled deliberately. They also help separate data quality issues from modeling issues, because sudden shifts in feature ranges can indicate upstream changes. The important idea is not the specific implementation, but the habit of checking whether you are still operating in familiar territory. When extrapolation risk is common, choosing simpler models can be a rational defensive strategy rather than a concession to lower performance. Simpler models often impose smoother, more constrained relationships that degrade more predictably when pushed outside the training range. Highly flexible models can contort themselves to fit training data extremely well, but that flexibility can translate into unstable behavior when extrapolating. In domains where future conditions are expected to differ meaningfully from the past, a model that is slightly less accurate in sample but more stable out of range can be the better choice. This is not an argument against complexity in general, but an argument for matching model capacity to the expected operating environment. The exam angle here is about reasoning under uncertainty, not maximizing scores in idealized conditions. High training accuracy is one of the most misleading signals in applied modeling because it tempts people to treat fit as proof of usefulness. Training accuracy almost always increases as model capacity increases, even when the additional capacity is fitting noise. Without an out-of-sample check, there is no way to know whether the improvement reflects real signal or memorization. In security-related problems, where adversaries adapt and conditions shift, memorization can be actively harmful because it locks the model into yesterday's patterns. Avoiding blind trust in training performance is therefore a foundational discipline, not an advanced nuance. The correct mental model is the training metrics tell you what the model can do under idealized conditions, not what it will do tomorrow. Time-based splits are especially important when the future is expected to differ from the past because they expose the model to realistic distribution shift during evaluation. Instead of randomly mixing past and future data, a time-based split trains on earlier periods and evaluates on later ones, preserving the direction of change. This makes evaluation harder because performance often drops, but that drop is informative rather than discouraging. It tells you how the model handles drift, seasonality, and evolving behaviors that interpolation alone cannot reveal. In many operational environments, this is the closest approximation to real deployment you can achieve during development. From a generalization perspective, time-based splits force you to confront extrapolation along the time axis explicitly. Communicating model confidence should include an explanation of where that confidence is strong and where it is weaker, based on region of feature space and time. A single global confidence statement hides the fact that the model may be reliable for common cases and unreliable for edge cases or new regimes. By articulating that predictions are more trustworthy within observed ranges and less trustworthy beyond them, you align expectations with reality. This kind of communication is particularly important when model outputs drive automated actions, because it helps stakeholders understand when human oversight is most needed. It also reinforces that uncertainty is not a flaw, but an inherent property of prediction under incomplete information. Clear communication about confidence boundaries is a hallmark of mature model governance. Planning fallbacks is how you operationalize the recognition that extrapolation increases uncertainty. A fallback might involve deferring to a simpler rule, escalating to human review, or abstaining from prediction when inputs trigger extrapolation checks. The specific response depends on the cost of action versus inaction, but the principle is the same. Do not force the model to decide when it is operating far outside its competence. Abstention policies are often misunderstood as weakness, but in high-risk systems, they are a form of strength because they prevent confident errors. From an exam standpoint, the key idea is that responsible systems anticipate uncertainty and define behavior for it in advance. Extrapolation without a fallback plan is an accident waiting to happen. The anchor memory for episode 85 is simple and deliberately blunt. Training shows fit. Test shows truth. Extrapolation is danger. Training metrics tell you whether the model can represent patterns in known data. Test metrics tell you whether those patterns transfer to new data drawn from the same distribution. Extrapolation is where neither of those assurances holds because the model is being asked to operate without evidence. Keeping these three ideas distinct prevents you from over-interpreting success in one area as success everywhere. This anchor helps you quickly diagnose why a model that looked strong during development may struggle after deployment. To conclude episode 85, titled Generalization, In-Sample versus Out-of-Sample, and Interpolation versus Extrapolation, state one guardrail that protects against extrapolation and explain why it matters. A clear example is implementing feature range checks that flag when inputs fall outside training distributions, triggering a fallback or review path rather than a blind prediction. This guardrail matters because it turns silent extrapolation into an explicit condition that can be managed, reducing the risk of confident but invalid outputs. Other guardrails can include time-based evaluation, simpler model choices, or abstention policies, but the common theme is acknowledging limits. When you can name a guardrail and connect it to extrapolation risk, you demonstrate that you understand generalization as a practical constraint, not just a theoretical concept. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.